So hello, everybody, and welcome to a new session of this Talent Q seminars that is under this umbrella of Quantum Spain. And today we have the seminar by Pablo Bermejo. He's a PhD student between DIPC in San Sebastián and Los Alamos in the US. And well, the research topics that of this PhD is about hybrid quantum machine learning for niche devices, analysis of quantum machine learning methods, attention networks, and neuromorphic computing. His background is starting in Madrid as an engineer, but he moved then to Paris in L'École Normale to do a quantum physics master. And then and now he's in between Los Alamos and San Sebastián for doing his PhD. Today, he's going to talk about quantum convolutional neural networks are effectively classically simulable. And so please, Pablo, the floor is yours.
Thanks a lot. Thanks a lot, Javier and Enrique, for the invitation. We are very happy to be here today presenting this work. I'm very glad to be part of this initiative. As Enrique was saying, I'm here to talk about our latest article that we put out on the archive last month by the name of Quantum Convolutional Neural Networks are effectively classically simulable. This is a work that I've done with this bunch of beautiful people here at the bottom of the slide. Paolo, who is a postdoc, a very clever one here at Los Alamos. Manuel Rudolph, also a very smart PhD student in the group of Zoe Holmes at EPFL. And then Lucas and Marco, who are the PIs of the Quantum Information Group here at Los Alamos. So before going into the details of my talk, I would like to remark that this is not intended to be highly technical. So this is mainly for you to grasp the reasons why we are pushing on this direction, why we are putting out this work, and for you to understand the questions that are arising from this whole idea of understanding simulability of quantum models, and well, to really look into future prospects of this work. So I guess that this is a broad audience. So let me first give a bit of context. As you all may know, quantum machine learning has gained a lot of interest lately because of the combination of the heuristic success of classical machine learning and the computational promises of quantum computing. So during last years, there has been this exhaustive exploration of both applications and architectures in quantum machine learning that could somehow bring some potential advantage over their classical counterparts. And this has happened in every single task you can think about, supervised and reinforcement learning models. And in this scene, there have been many models that have enjoyed some special attention. And this is the case of quantum convolutional neural networks that we are talking about today. And before getting into the reasons why this is classically simulable and what this implies, let me explain a bit why this is the case, why QCNNs are so popular in the literature. So you may all be aware of the fact that quantum machine learning models are not for free. They have limitations. They have trainability barriers, such as barren plateaus and local minima. Well, this is bad because this forbids some applications of our quantum machine learning models, but apparently, happily for us, this is not the case for QCNNs, because QCNNs were proven to have absence of barren plateau. It is on this paper by Artur Presa and people from here, from Los Alamos. Because of its topology, it is also suitable for near-term devices, which is quite good for implementation concerns. And also, it has shown heuristic success for most datasets employed in the literature. So this all has caused that nowadays the use of QCNNs is very, very spread in the community. And people are still today pushing towards this architecture for getting better and better applications in quantum machine learning. And this is quite good, right? Because we are talking about an architecture that do present absence of barren plateau. This is awesome because apparently this implies that we can train our models, we can successfully apply to almost any quantum machine learning task we can have in mind, but this is not a freelance theorem or a freelance statement. And as we posed in this article last year, this absence of barren plateau might come with some caveat, which is its classical simulability. And more in depth, what we say here, what we claim, is that the features that lead to provable absence of these exponentially vanishing gradients, this is the definition of barren plateaus, serve as blueprints for classical algorithms that can simulate the action of this model. And this is important, provided that one is given access to an initial data acquisition phase on a quantum computer. So this is the very premise of our current work, the QCNN work. And in case you are more interested in getting the basics of this other work, please go to Zoe's talk, Zoe Holmes, who gave a talk in this very series of seminars about this claim. Okay, so this particular statement is a statement in average, but here, for this new work, we were interested in pushing this further. We were wondering if we could do better and, well, not only simulate randomly sampled points of a barren plateau-free model, this is the meaning of doing it on average, but also replicating a successful training over a simulated landscape. So in this work, what we are doing is that we are arguing that the action of a unitary QCNN is simulable. But this is not just a statement on average, but in the stronger sense of enabling successful training by using a classical algorithm and enhanced with classical shadows, which are these measurements out of a quantum circuit. So this is like the main idea of our work. So how are we doing that? How are we showing that QCNNs are effectively classically simulable? Here, I will prompt the very basic ideas that I will detail afterwards in a few slides. But for you to have this rough intuition, in order to understand the simulability of QCNNs, we have first to conceptualize, to characterize its success. And this is done by answering these two main questions. The first one concerns how a QCNN processes information. How does it look at operators in a quantum circuit? And the second one is linked to the applications where the QCNN is applied. So how do datasets look like? What are we feeding the QCNN with? Answering these questions will allow us to provide numerical tools capable of simulating the action of the QCNN, given, and again, this is important, that we have access to Pauli classical shadows on the dataset states. First of all, before moving forward, a disclaimer, our results that I'm showing here today showcase that the heuristic success of QCNNs appears to be tied to particular datasets. Of course, one could come up with some examples where this classically simulable regime no longer holds. For example, as I write in here, embedding some cryptographic assumptions in our QCNN. See, for instance, this paper about how to do that by Ellis Hilfuster. But we think that these are mathematical artifacts rather than realistic practical problems. And for our concerns, this is left out of our work. Okay, so we know where we come from, we know where we're going, and now I would like to talk about the very basic ingredients of our work. We are talking about QCNNs, but let me first get what a QCNN is and what kind of problems in QML, in quantum machine learning, we can tackle with a QCNN. So starting by the later, because it'd be useful for definitions of classical simulability, let me say that it is often used for supervised QML, for example, classification of phases of matter. And in order to be able, as I was saying, to define classical simulability and get a bit more technical, let me just define a few terms that dictates what a supervised QML algorithm or task is about. So here we will have a few elements. We will have a data space that we denote by R, belonging to some space of quantum states within an n-qubit Hilbert space. We will also have an integer valued label space, and we will have an unknown function mapping between the two. So taking states out of our data space and assigning some label to each of them. The goal is simple. As in classical machine learning, we want to optimize the parameterized function that we call H to approximate the labels produced by F. How are we doing that? The method? Well, we are training this function by having repeated access to a data set where the data samples are drawn from this data space according to some probability distribution, and each of these samples is associated with some label. In our case, we are using two kinds of data. We have classical data, where the states in our data space are produced by encoding some real-valued classical vector into a quantum state by means of an encoding map. We'll see what this map is about, how to perform it. And then quantum data, where the states in our data space is produced by some quantum mechanical process of interest. One can think about preparing some quantum state on a quantum circuit and taking some measurements out of the quantum circuit. Okay, so then what is a QCNN? First, rough sketch of it, just the main idea. It is an architecture composed of a sequence of convolutional and pooling layers. The convolutional layers, for those of you that are not familiar with it, are used to coarse-grain information out of the input quantum states, and the pooling layers are aimed at reducing the QCNN's feature space by tracing out, by discarding some information out of these registers. So here you have some pictures of what this looks like. Picture B is, for example, a QCNN where the convolutional layers are composed of two local gates acting on nearest neighbors, and the pooling layer traces out half of the qubits. Since we will need to, again, be more technical in order to understand the framework of classical simulability and how it links to these types of supervised quantum machine learning, let me define the QCNN more properly and introduce some assumptions that will be used during our work. More formally, this QCNN is the composition of quantum channels of the following form, where you have CMP that are parameterized channels representing convolutional and pooling layers. Once again, the convolutional maps preserves the size of the quantum registers, and the pooling maps reduce the size of them. Of course, one could think about many topologies corresponding or fulfilling these requirements, but here, in what follows, we will assume that these convolutional maps are just unitary evolutions parameterized by some theta parameters, and the pooling maps will no longer be parameterized and will be just used to trace out some qubits to get rid of some information along the quantum circuit. On top of it, we will have an output of this quantum neural network where we will measure an observable acting on order 1 qubits. This is 1, 2, 3 qubits, depending on the size of your system, and assigning the predicted label, which is calculated as follows, as in any typical classical machine learning algorithm. We will have the trace of our evolved state and the application of the observable, in this case, we have it O, that will be used to calculate some loss function that will dictate how close predicted labels are from the true ones for some training data set that we call T. The parameters inside the QCNN will be solved by means of resolving this optimization task, where we calculate the optimal parameters that give rise to some trained model where the optimal parameters are embedded in the QCNN. The important thing here is that in a typical QML setting, one assumes that calculating these labels requires a quantum computer. So one assumes that this task is hard to simulate. But if a model is classically simulable, then the implementation of its parameterized quantum circuit on a quantum computer is unnecessary. And this is what we are claiming here for the case of the QCNN. Okay, so I didn't mention it at the very beginning, but in case you have questions during the talk, just raise your hand, turn your mic on and shoot it. You don't have to wait till the end of the presentation. So any questions so far about the framework, about what we mean by QCNN, what it is used for? Okay, I take it as you are clever people, so let's move forward for the definition of classical simulability and what we mean by classical simulability, which is the core of our project. So traditionally, this classical simulability is linked to the existence of an algorithm taking an efficient description of the problem. This is an efficient preparation of some state, the operations in the circuit, and an efficient representation of some measurement operator, leading to the estimation of a loss function. What is important here is that in this framework, in the classical framework of classical simulability, the traditional one, the performance is measured based on the error given by the difference between the estimated loss function and the original loss function for some set of parameters theta, or instead the expected value of the difference between the two over the whole landscape. And this is cool because it shows that random points in the QCNN's loss function landscape are classically simulable with high probability, but still it does not imply that we can simulate regions of the landscape that are relevant during training. This is that allow us to get high accuracies for the problems at hand. So here in this work, we will follow a more pragmatic definition driven by solving this task of interest by achieving high accuracies for our applications. In order to do that, we will follow the setting presented in this thus provable absence of barren plateau article by Marco, where we use a classical simulation enhanced with efficient shadow tomography. More in detail, how does this setting look like? Well, in here, we will have access to a quantum computer for an initial data acquisition phase. We will be able to prepare copies of the states in this data space. We will be able to apply some operations on these states and measure them via some efficient tomographic classical shadow techniques. Very important, once this data acquisition phase is over, there's no longer access to the quantum computer. And this is given in this picture on the top right, what we call SysMQE, the SysMQE framework, where you have your quantum computer in order to retrieve some data out of it. And once you have this data, you no longer access the quantum computer, and everything else is done on a classical device. And the optimization process is carried out in this classical computer, as opposed to the QCM framework, where you can access the quantum computer for its iteration, its optimization step inside your algorithm, and not only for the data acquisition phase. In here, we will say that a model is classically simulable if there exists a classical algorithm that first takes a simple and efficient description of the problem, plus some data from our quantum devices in initial acquisition phase, and then it returns the estimation of the loss function such that the solution of the optimal parameters allows for building a trained model that gives classification accuracies that are close to the original function. This is not focused on the loss function, but the accuracies, as you see. And this definition is very tied to the notion of dequantization in quantum machine learning given by Elias Hilfuster, this very same article, where we only add the access to measurements obtained from a quantum computer during this data acquisition phase. The main claim of our work is that there is no need to run a parameterized quantum circuit on a quantum device, and one can consider that its information processing capabilities, the information processing capabilities of the model we are dealing with, are dequantized. And probably this picture defines or explains better than me what I just said. Instead of running a quantum circuit with the embedding of the QCNN, just collect shadows at the very beginning of your algorithm, and then run everything else on a classical machine, because you have no need to go back to your quantum circuit and spend those quantum resources during your optimization steps. Okay, so once we understand the framework in which QCNNs are used, now we have to understand why are these so successful. So we have to dig a bit deeper into these questions I was posing at the very beginning of the talk. Why? Because, spoiler, conceptualizing this success will be very useful and will be key to know why we can explode these issues to go for this classical simulation of the action of the QCNN. So the first claim was about understanding how QCNNs process information. And this is related to a statement about randomly initialized QCNNs. So let me introduce a few terms that will conclude on some informal result. If we denote by phi this Heisenberg evolved measurement operator, the evolution of the operator O throughout the circuit, we expand this operator in the Pauli basis and define bodyness of any Pauli as the number of qubits it acts non-trivially on. And finally, we assume that when initializing the QCNN, we sample the parameters such that its local gate forms an independent local 2 design over U4. What we find by means of Weingarten calculus is this informal result that in average, the contribution in phi of a given Pauli with bodyness K decays exponentially with K. Or in detail, if we define these quantities called k-purities that we call k-purities, which are the projections of a given observable into all the Paulis with bodyness K. This is the mathematical formula for it, where if the observable O has norm 1, then the sum of the probabilities is equal to 1, and each single term inside this summation is positive, so the k-purities form a probability distribution. If we plot the normalized average contribution of each Pauli with bodyness K to the k-purities, what we find is the following, that it indeed decreases exponentially. So in our work, we make this analysis by analytical means, but in case you want an efficient numerical algorithm to compute the k-purities for an arbitrary circuit topology, an arbitrary group, take a look at this article by Pablo on computing exact moments of local random quantum circuits via tensor networks, where we more deeply define this concept of bodyness, and we introduce some cool numerical tools for the purpose of calculating these k-purities. So this might sound a bit abstract, so let's try to take it to the ground and understand what is the consequence of this way of processing information by the QCNN. So if we are trying to compute some traces like this one, where we have rho and the Heisenberg evolved operator, what we are finding is that the dominant contribution in the predicted labels arise from order 1 bodyness measurements over your initial state. So that when randomly initialized, the QCNN will start its training by only processing information encoded in this polynomially sized subspace of low bodyness observables in their input data. This is linked to the proof of absence of barren plateau by Arthur Pesa, where they say that large components in the loss functions gradients arise from local terms in the Heisenberg evolved measurement operator. And you see that the very thing that the very fact that makes QCNNs absent of barren plateaus, it is what allows us to simulate the action of the QCNN because of this polynomially sized subspace. And this result is strengthened by our companion paper by Armando Grisani and Marco and Robert Juan and people from EPFL. Well, they find that on average, the error in approximating the predicted labels via this phi or by low k-value approximations of this operator decays exponentially with k. For many architectures, you can check it out. It's a very cool approach. Of course, one could think that local observables over the initial state can be exponentially suppressed if the input data is too entangled. But in this case, we fall within the barren plateau regime, and the assumptions of our trainable QCNN do not longer hold. So this was our attempt to answer the very first question: how does a QCNN process information? But if you remember, there were two of them. The second one was related to what are the data sets that are feeding the QCNN with. And we claim that those data sets are locally easy data sets, defined as follows. Given a data set for a supervised quantum machine learning classification task, we will say that it is locally easy if it can be classified by the information encoded in low-bodyness observables of the input states. Having a locally easy dataset is necessary condition for the optimization curve to lie within the low-bodyness subspace, but it is not a sufficient one. It could be possible that there exists initial points connected to the global minima through paths that need to leave the subspace. This is our intuition about it, right? However, we compile many classical and quantum datasets in the literature to benchmark QCNNs that are used to benchmark QCNNs, and we find heuristically not only that these datasets are locally easy, but that the classification task can be solved by remaining in this low-bodyness subspace. So you don't really need to leave this subspace in order to achieve high accuracies for your tasks. This is schematic representation of our main results. The summary is that we have the QCNNs that do only look at input states within this low-bodyness subspace. But on top of that, we are feeding the QCNN with use cases that only require of that small size subspace, polynomially sized low-bodyness subspace, in order to achieve high accuracies, so perfect match. And that explains the success of the QCNN. And this leads to the fact that there exist efficient classical algorithms that can simulate the action of the QCNN in this small subspace, provided that we are given access to Pauli classical shadows on the input data. This is the summary of what I just said. If the QCNN achieves high accuracy, it is surely locally easy dataset. So let's move towards the numerical results for our simulations, for our claims. As argued before, a brief summary, we are saying that the QCNN simulability occurs because of the fact that they are initialized, explored, and in their training in the polynomially large subspace of low-bodyness observables. So we can simulate QCNNs and dequantize its information capabilities for essentially all datasets in the literature. The main purposes of this section are three. First of all, we want to prove that the datasets that one commonly encounters in the literature as heuristic evidence for QCNNs are locally easy, so that simple Pauli classical shadows are enough to extract the relevant features out of this data. Second, we want to illustrate the classical simulation of QCNNs, as well as the scalability of the proposed techniques that we include here in this work, where we simulate the action of the QCNNs up to 1,000 qubits. And lastly, we want to study how the performance of the simulated QCNN depends on the number of measurements, the number of shadows, used during this shadow tomographic procedure. So what techniques are we using for the simulation? Well, we employ two different methods, which are constructed to only process the information encoded in these low-bodyness measurements of the input state. In particular, they accomplish this goal by truncating the Heisenberg evolved measurement operator to bodyness of order 1, which allows us to guarantee an efficient representation of this backwards evolved operator. For the quantum datasets, we are using low-WISA that I proceed to explain after this slide, because I think it is useful to have this notion of, to clarify this notion of barrenness and backpropagation of an operator. And we are also using constrained barrenness tensor networks for classical datasets that do follow the same pattern, the same idea. This will showcase the diversity of classical methods that enable the simulation of the QCNN action, as well as their broad applicability. And a remarkable fact is that in all cases, we find that the simulated QCNN reaches similar or better performances than those reported in the literature for what we dub full QCNNs, which is QCNNs that are not restricted to the subspace of low-bodyness observables. More importantly, we show that our finite sample shadow-based simulations cannot perform full QCNNs trained with no finite sampling. So let's understand this tool, this low-WISA tool. Low-WISA belongs to the family of Pauli propagation surrogates. So first of all, what is Pauli propagation? It refers to the simulation of an expectation value in the following form via a Pauli path integral approach, where we apply a parameterized quantum circuit, is U in here, to some observable in the Pauli transfer matrix formalism. One can show that after the entire quantum circuit, we receive a weighted sum of Pauli operators defined as follows, with some summation over Paulis accompanied with some trigonometric coefficients that are polynomials. This is all shown on our article and also on other works where low-WISA was included. If we write our initial state as also a summation of Paulis, we come up with the following expression for the observable O. That will be useful to define some truncations employed in this low-WISA algorithm. So I move forward to say that the advantage of this framework is that we can restrict the simulation to this polynomially small operator subspace of low-bodyness operators by truncating a Pauli path if the propagating Pauli operator crosses a truncation threshold. And in this context, how do surrogates emerge? Well, this is the very same equation I was prompting before. In this case, for surrogates, we know the initial states beforehand, right? So we can calculate this coefficient C beta and the trace P beta and P alpha before any optimization of theta, because those are independent of these variables, right? So we can invest pre-computation time to identify which indices beta are most important to the task at hand, and then only evaluate along the Pauli path leading to those Pauli operators P beta. I recall that in this work, we use measurement of our data states in random Pauli basis so that we can express the expectation values of our observable as follows. And then we can make some truncations out of it, where there are a few more than what I am showing here, but these two are the most important ones. First, we can restrict the propagation to low-bodyness operators. The operators P alpha have at most this threshold bodyness K, which I show here on this picture. Imagine that we have L layers, so we are backpropagating this measurement at layer L throughout the quantum circuit. This is, you can imagine qubit 1 and qubit 2, and the circles are the operators acting on each qubit, where this bunch of guys is just like a superposition of operators applied on a single qubit. And you see that whenever you have 3, for the case of bodyness 2, for example, whenever you have 3 or more operators, you cut it off and you get rid of the extra terms, constraining your evolution to this subspace of operators with bodyness 2. One more truncation you can perform is the frequency truncation, which affects the degree of the polynomials in C alpha, and this erases high frequency features of the loss function landscape, which is also useful to reduce the computational complexity of your problem. So getting into the use cases. First, we are starting by the quantum datasets. As I was mentioning before, the QCNN is employed for the classification of phases of matter. In the standard test cases, just to demonstrate QCNNs, the local information encoded in low-bodyness measurements suffices to classify the state, as we will see. So we can train a simulated QCNN using the Louisa-based Pauli propagation methods via Pauli classical shadows on the dataset states that are obtained, for example, via DMRG. In our case, we are employing a generic QCNN with 2-qubit unitaries and 15 parameters defined in its gate, and we trace out half of the qubits in its Pauli layer, very same as the picture I was showing at the very beginning. We are focusing on 4 models, which are the most employed ones in the literature. This is the one-dimensional Heisenberg bond-alternating XXS model for 1,000 qubits, the Haldane chain for 500 qubits, the axial next nearest neighborizing model, and the cluster Hamiltonian, both of them for 32 qubits, in order to compare with some results that were already there in the literature. So let's start with the Heisenberg bond alternating XX model. This is the Hamiltonian of the model, where X, Y, and Z denote Pauli operators acting on the ith qubit, and where Ji stands for J1 or J2, depending on if you are on a qubit which is even or odd. That's it. So in the thermodynamic limit, the ground state of this model presents a phase transition controlled by this ratio J2, J1. This is the phase diagram. Here we are using a data set of 100 states, and the results are averaged over 5 different runs. And what we find is that the model is classified with bodyness K2, and within the whole space of initial data sets, we are using just 400 operators to define its sample in this data space and backpropagating those throughout the quantum circuit, which is a quite low number if you think about it in 1,000 qubits. And this is the contour plot, the heat map for the results. Y-axis is the number of training points out of this data set with 100 states, and x-axis is the number of shadows, the number of individual measurements you do at the very beginning in your data acquisition phase. And you see that you can very much classify your model having access to 100 shadows and 20 training points with accuracy 100. And I want to recall that what we are doing here is that we are running our quantum circuit, doing some measurements out of it, and once we have this data, we are moving everything to the classical device. So the only quantum resources that we are spending here can be calculated by the number of shadows times the number of training points, because this is the number of times we have to run our quantum circuit. And we do not have to use the quantum circuit for any iteration, any optimization step throughout our minimization process, throughout our classification task, just during the acquisition phase. So for the Haldane chain, we have some similar results. This is the Hamiltonian defining the model. Here we take J to be positive. We know that in the thermodynamic limit, the ground state presents 3 distinct phases controlled by the ratios H1 over J and H2 over J. Here, we want to make a binary classification. We leave the whole phase diagram classification for the ANNI model and the cluster model. So here, we are fixing J equals 1 and H1 equals 0.5. And we are trying to distinguish between the paramagnetic and the symmetry protected topological phase. We are using a data set of 100 states, and the results again are averaged over 5 different runs. Here we find that this model is classified with bodyness K3, and this is again the heat map for the result. As you see, the order of magnitude of the shadows and the training points is the very same as the XXS model, proving that this is a very simple task to perform, this classification of the Haldane chain. We move towards more interesting results. the NNNI model so that we try to classify or to distinguish the whole phase diagram. So this is the Hamiltonian. In the thermodynamic limit, the ground state is dictated by some non-dimensional parameter kappa and 8. Here we fix J1 to be equals to 1, and we try to define the whole phase diagram, classifying between 4 phases in our phase diagram. We are doing this with a data set of 300 states, and the results are averaged over 5 different runs. In this case, the model is classified with bodyness K4. And as you can see, with just 20 training points, you can very much gain a lot of insights into your phase diagram, achieving accuracies that are close to 80%. For you to have a reference, previous attempts to classify this model using QCNNs were achieving results in the vicinity of 70%. So I think that this showcases as well the simplicity of the task we are facing here. Lastly, we go for the cluster Hamiltonian. Here we have the Hamiltonian defining the model. In this case, in the thermodynamic limit, the ground state is dictated by the ratios between J1 and J2. This is the phase diagram. Here, once again, we are using data sets of 300 states, and the results are averaged over 5 different runs. And once again, this model can be classified with just bodyness K4. For you to see this, you can again take a look at the classification result, where barely 20 training points are enough to get around 80% accuracy in the classification task. Again, for you to have a rough intuition of previous results, with 20 training points using QCNNs, full QCNNs, people were achieving results close to 75 or 70% accuracy. And also, I didn't mention it, but in the case of the ANNI model and the cluster Hamiltonian, we are using around 3,000 shadows for each of the tasks. Finally, for classical datasets, what we find is that we can show that the most commonly used classical datasets in the literature are locally easy. In order to prove that, we try to classify the MNIST, the Fashion MNIST, the Eurosat, and the GT-SRB models, and we study the simulation of the QCNN with both amplitude and angle encoding. For amplitude encoding, we load its image in the dataset at hand as a square matrix of floating point values, or triplets of them in case of color data. If needed, we merge the color channels into a single grayscale matrix. After resizing this matrix based on the dataset, it is reshaped as an unnormalized quantum state on 8 qubits. Even if the pictures are bigger, you don't really need more than 8 qubits, which is also a symptom of how easy these tasks are. And lastly, we normalize the quantum state and encode it in an MPS, in a matrix product state, tensor networks, by SBD. For angle encoding, we will use a tensor product embedding, hardware efficient embedding, and the so-called classically hard embedding. To allow for the QCNN's trainability guarantees, we will need these encodings to be shallow so that we already have an efficient MPS implementation of these embedding methods. This is the table of results for the classical datasets we used, and you can see that you can barely reach 95, 100% accuracy for all the models with just bodyness 2. This all is bodyness 2 except for this star thing, which is bodyness 3. But here you can already see that, unlike the quantum dataset case where the dataset states preparation could be hard to simulate, thus requiring shadows, all of the quantum machine learning models used here are fully classically simulable. The embedding is an MPS, and then you can simulate the action with tensor networks. As such, it appears that no quantum resources are needed to simulate the QCNN in these cases. This implies that using QCNN-based QML schemes for classical data appears to be an ill-motivated task. So conclusions. First, we show that the QCNN appears to only work on easy problems for which the action can be classically simulated. There is currently no evidence that QCNNs will work on classically non-trivial tasks, so we should reconsider the place of QCNNs within promising QML architectures. But on the bright side, there is not a full dequantization of QCNNs. However, the resource requirements, classical shadows that we are using here, are substantially easier than running the QCNN on quantum hardware. We also foster quantum measurement enhanced machine learning via this mix of classical shadows and classical simulability. And this setting of classical training can be also embedded in classical training plus quantum deployment. This is the training of a QCNN on a classical device via classical shadows, and then the use of the optimal parameters to implement and test the model's performance in a quantum computer on new data without using shadows for that new data. The results and lessons that we get out of this work can be applied to quantum machine learning more broadly, as Armando showed on his paper. So one can envision that all the circuit architectures that are average case simulable could also be classically trained via low-bodyness operators. And we argue with this all that our community might be in dire need of non-trivial data sets. And with this all, I conclude my presentation and I take any questions you want. And sorry for the interruption. I don't know what happened. Maybe they wanted to shut me down.
Thanks a lot for the presentation, Pablo. Now it's time for the audience to raise their hands and start the comments, questions. Alba, please.
Hey, thanks, Pablo, for this very nice talk and very nice work as well. My question is regarding how do you simulate these super large quantum convolutional neural networks? And also, sorry, let me start again. So this convolutional neural network architecture resembles to MERAS, you know, this tensor network formalism. So did you find some kind of equivalence between convolutional neural networks and MERAS? And also, why did you use MERAS for the simulation? Because as far as I understood, your simulation algorithm is based on other type of techniques.
Yeah, the thing is that as people know in the tensor network community, MERA is very related to QCNNs, but still not the same because of the input state. So in MERA, you need an efficient description of your problem in this tensor network format, which is not the case for QCNN. In QCNN, you can have more general descriptions of your input state. So what we are saying here goes a bit further because what we are doing is restraining those general quantum states to this low-bodyness subspace. And this is what makes the QCNN simulable. It is not that it is related to MERA. If you do something like MERA, you could no longer generalize your results to most datasets in the literature because the main point has to do with this low-bodyness subspace, not with the relationship with tensor networks, first thing. And then I guess that this leads to the answer to your question, which is we cannot constrain our simulation using MERAs. We need something else. And this is why we go for Louisa, which is basically applying the topology of the QCNN, MERA-like, of course, but doing this truncation of operators on the fly. So it all comes, or the main point is how you process information and what datasets you are using, you are feeding your QCNN with. So using MERAs would not be enough. That's the short answer.
Okay,
is that answering your question?
Thanks.
Sorry, Alma?
Okay. Yeah, understood that thing you just answered the question. Thank you.
Thank you.
Any other question? Elias, please.
Hello, thanks for the nice talk. It was really interesting. You were mentioning the need for non-trivial data sets. So do you have any idea how this may look like?
That's a great question. That is something we are also interested in. That is something that we as a community should look into, because we were trying to, we were trying to look into more complex data sets, as in topological data sets, topological phases of matter, and so on. And still they fall within this regime of easy data sets. So that's a great question. We are not sure about the answer. We are yet not convinced about where we should look at, but it's definitely one of the main questions arising from this work. In case any of you has any idea about where we should look into, or want to propose some, I don't know, crazy model to test this QCNN to see if it is classically simulable, and so on, we're happy to hear, because we don't have any clue about that.
Okay. The thing is that it reminds me somehow of these works in which some artificial data sets were used to show some kind of quantum advantage of some models. For instance, quantum support vector machines. If you remember this work by people at IBM, they kind of created this data set which was easy for the quantum kernel and difficult, or allegedly difficult for the classical kernel. But this seemed to me, or for instance, you have data sets which come from factoring problems. Okay, you can somehow embed a factoring problem into a data set, which is, well, supposed to be very difficult for any classical model. But to me, these are kind of artificial. I don't know if you can use some similar technique, but then even if you can do that, I'm not sure what this would mean for practical quantum machine learning, because it's not clear that you would find this in a natural problem.
Yeah, I completely agree. I don't know if you were at the very beginning of the talk, but I was precisely highlighting that disclaimer that here we want to focus on realistic problems, and you can very much embed these cryptographic assumptions or factoring assumptions into your QCNN. And we don't know, maybe it falls out of this classically simulable regime, but we don't think that's realistic. I don't know if it's worth it to push on that direction, because it is outside of what people are doing in the community. And yeah, it is simply not realistic, maybe. So
I connected a few minutes late, so I missed this. Sorry.
So no, it's a super good question. I mean, it's very much of our interest. Yeah.
Thank you.
Yes, please.
Hi, Pablo. Thanks again for this amazing talk. So my question is somewhat related. So this classical simulability via low-bodyness operators is related to data sets. And as you said that we need more complicated data sets which are hard to simulate, right? But can it also depend on different kinds of encoding methods? Like not the data set, but how you encode them into the quantum circuit. You showed that by angle encoding and amplitude encoding, they are still classically simulable. But can we maybe come up with the different encoding methods that serve the purpose?
Yeah, that's also an interesting question. But as I was mentioning before, probably the fact that you can cover pretty much everything with this amplitude encoding or this angle encoding is because if you try to do some fancy stuff, you will go for some not shallow circuit in order to embed your information, and you will no longer have guarantees about your trainability, the trainability of your model. So here we want to work within this assumption that you can train your model, you have absence of barren plateau, but this is no longer certain if you try for something else. Plus here we are pretty much covering everything in the literature. So for classical data, we are mostly sure that you don't really need anything else. And for quantum data, we have proved that with classical shadows, which are just measurements of your states, you can perform the classification task. So yeah, concerning your question, doing some more complex stuff, I don't know if that's worth it. I don't know if it could be useful for the implementation, because you may fall within this non-trainable regime, the barren plateau regime, and maybe you don't get any advantage over the amplitude and angle encodings.
True.
Is that answering?
Yeah. Yes. Thanks.
Yeah, thank you.
Any other question? Yeah. Please. You should unmute.
Hello. So thank you very much for your interesting talk. So I believe that you have run your quantum circuit, which is the QCNN, on a classical computer, right? If it is the case, have you examined the effect of quantum noise on the QCNN and how it influences its simulatability?
No, not here. We didn't do that. No.
Okay.
It's also, maybe it's a good question, but in this case we stick to this noiseless regime. Yeah. So maybe I don't know. Yeah. Maybe Marco wants to add something in this regard, or I don't know. Or maybe he's not here.
Thank you very much.
Yeah, thank you.
Any other? So just let me ask you a final question, is that more or less you use this QCNN to phase classification, no? The different phases that of this model that you were showing. And then you are telling us that these QCNN are classically simulable. Also, you said that for this classification, you use these low K operators, no? This to describe the information that we need. So all in all, will you say that phase classification is an easy task?
As in a general sense, or? Yeah, that's probably the case, because even, I mean, probably one of the most complex problems one can think about in terms of classification is topological states, and even those are seen to be classifiable via this low K thing. So that renders the question of that maybe classification tasks or supervised classification tasks are simple. What happens if you don't have any reference states? If you go for unsupervised learning, that's another question. But if you have these training samples, I do believe as of now that it is simple, or everything, the evidence is pointing out that it is simple. As I was saying, as I put out also this work as a challenge for the community, in case people come up with with some difficult data sets, that would be great. So Marco?
Yeah, please. I think he disappeared. I don't know. Okay.
Oh, hey, for some reason, I wasn't able to unmute my mic and I had been struggling for a bit. Just wanted to give the previous comment on noise that we're working on it. And I think that noise actually makes things way easier to simulate. So I only think that noise will make the problem like much easier for classical computers. And this goes back to some of those results by Dorit Aronov's of simulation of noisy quantum circuits. So yeah, in general, I would say that the noiseless case is the hardest. So noiseless is already kind of like easy to simulate. And when you throw noise into the mix, it's going to be like even easier for sure.
Yeah, so for an average case, it's easy to study, yeah. You also have these papers from Miles Turemeyer about how to simulate noisy quantum circuits. And they say that whenever the noise threshold is below some percentage, you can basically go for a very large polynomial size and a very large polynomial depth of your quantum circuit. So as Marco was saying, that's for sure. Noise makes things simple, but we didn't work it out for this project. So yeah.
Okay, if there is no other question or comment, we will thank again Pablo for this nice seminar, and then we will meet in the next seminar of Quantum Spain in a few weeks. No? Thanks a lot for connecting.
Thank you.